Elena Grewal did an outstanding job at the WiDS 2018 conference, sharing insights on how Airbnb leverages massive amounts of data to make business decisions and improve the user experience. It was one of my favorite tech talks that year. I really appreciated Elena's explanation about how cross-functional teams at Airbnb innovate with technology in 3 areas: analytics, algorithms, and inference. She gave some great examples of leveraging machine learning in areas such as customer service, risk modeling, and pricing strategies. In this talk, Elena gives an honest depiction of the challenges in deploying these solutions, as well as the successes that she and her team have achieved so far. I think you will especially enjoy her final comments regarding her philosophy, which she calls the Tao of data science.
Amazing. So I am so excited to be here today at this amazing conference. I'm in awe of our conference organizers for putting together this program and for thinking of this way to scale the program with these events all over the world. Very creative. So my goal today is to share a little bit about how we've used data science at Airbnb and the ways that we've used innovation in data science to inform our company's strategy and to improve the experience of our users. I hope that I'll give you some ideas and also paint a picture that everything that I'm sharing today is something that's an iteration on a prior attempt that maybe didn't go so well, and that there'll be more iterations in the future to come. So to start with, I'll share a little bit about myself. I joined Airbnb in 2012. Before Airbnb, I was actually right here at Stanford doing a PhD in education. So when I joined the company, we had 5 data scientists. Now we have over 130, so a ton of growth in this time period, and I've been honored to lead the team for about 2 years now. So I always like to start talks with understanding if our audience has used Airbnb before. So raise your hand if you have traveled or hosted on Airbnb in the past. That's amazing. OK, what are some locations that you've traveled to on Airbnb? You can just shout it out. Madrid, Iceland. OK, I like Aspen, Hong Kong. This is amazing. Tel Aviv. This is so great. So New Zealand. OK, we could keep going. These are amazing destinations. I'm staying at a wonderful host's place right now in this Bay Area. He has lived in his home for 40 years, and he rents a cozy attic apartment out, which is filled with vases of cut hyacinths that he's cut from his garden, and it smells divine. So some fun facts about Airbnb. We launched our Chinese brand last year, iBeing, and we're growing really rapidly in China. So if any of you shouted out a destination in China, that's very exciting. We also launched trip experiences, activities you can do on your trip in addition to a place you can stay. And this is also global and enabling people around the world to share their passions and be entrepreneurs. Tom Friedman wrote last summer that I wouldn't be surprised if in 5 years, Airbnb is not only the world's biggest home sharing platform, but also the world's biggest job platform. So a lot of exciting opportunities ahead. To give you some sense of the data, we've had about 300 million guest arrivals on Airbnb. We have about 4 million homes on Airbnb in 191 countries. So now let's talk about data science. We think of data science as one of the 4 legs of the stool of product development. So that would be design, engineering, product management, and data science. So we work very cross-functionally with our partners in an embedded, kind of matrixed organizational structure. We also recently evolved to organize our team around 3 tracks of work, which represented 3 kind of unique areas that we saw in data science at the company: analytics, algorithms, and inference. So throughout this talk, what I will do is talk to you about a concrete example of innovation in each of these 3 tracks, and then also speak about ways that we're scaling the work in these 3 tracks. When I think about technical vision and innovation, I also think about the ways that we use technology to automate and scale our own work. So let's start with analytics. What is a problem that we can solve with analytics? So the problem I'm going to pose for you is that simple customer support issues appear to take too long to solve. So you call Airbnb, and you will be received by an agent. And if you're on a trip, you might be received by someone who's a trip agent, who has expertise in answering questions for people on trips. If you're not on a trip, then you'll be received by a non-trip agent. And the idea here is that then you can get your question answered appropriately. And we also had the hypothesis that if you're on a trip, your problem might be more complicated than if you're not on a trip, where maybe your problem is, I need to change my password or find a button to change my price, and that's a little bit simpler to solve. So we started measuring how long it was taking for tickets to solve. And part of the innovation here is also an innovation in the measurement. So previously we had how long phone calls lasted, and we realized that was an incomplete signal on how long it would take to solve a ticket, because our agents were on the phone, but they were also following up over email or doing research on their laptops, and so there was a lot more that went into solving a ticket than just talking to someone on the phone. So we implemented what we call heartbeat logging, where we essentially ping a server at regular intervals with metadata on what an agent is doing at that time. And that enables us to then have an accurate picture of how long an agent is spending on a given ticket. Now, when we got that accurate data, we noticed this very interesting phenomenon, which is that the non-trip agents who were solving what we thought were more simple issues were taking 29% longer than the agents who were on the trip issues. So why do you think that was the case? What was going on? Well, that's where we use analytics. So an intrepid data scientist said, let me look into this data and understand what's going on here. What are agents spending their time on, and how do we break this down to know what is the reason it's longer? So this chart shows the non-trip agent's time and the trip agent's time for closing a ticket. And you can see that the red area is the amount of time that they're spending closing a given ticket, and it's actually quite similar and not much longer. However, the non-trip agents, for every ticket that they close, they're also doing a lot of other things. And in particular, we see this blue and this green, which represents time that they're spending on escalating the ticket. And that means that they got a ticket and they didn't quite have the expertise to solve it, so they needed to send it to someone else who did have that expertise. And that was taking a lot of time. So this is a really powerful insight for us to understand. And because we knew this, we were able to then think, okay, what's a solution to this? And we decided to create a new team of data scientists focusing on building machine learning models to effectively route the ticket to the right agent, so that when you called, you would go directly to the person who knows how to solve your issue and not necessarily need to have the time in escalation. So this was a great innovation for us and shows the power of analytics. So now let's talk about scaling analytics. In 2012, when I joined, we were in the YOLO phase. We had messy data. It was very difficult to figure out what was going on. Then we progressed to 2014, where we created a stable data warehouse called Core Data. And our most recent iteration is called Global Metrics. And the insight here is that we have a stable data warehouse, but a lot of our power comes in defining metrics and having single sources of truth for metrics. Our vision is universal, monitored, and accessible data. And the idea would be that you can write in a config file the metric definition, automatically generate dashboards, and have this be integrated into our experimentation framework. So this is something that we're going to see more and more as companies become more rigorous about metric definition, and as there are more people who need to define a metric, and you want to make sure you have the same definition. OK, so now let's talk about algorithms. I mentioned that in the past example, we had built out a team to work on ticket routing. Another challenge that we have in algorithms is around risk modeling. And the problem that we faced was that our risk models were losing information. So when you signed up on Airbnb, we would run a model and say, are you suspicious or not? If you logged in, we would have another model. If you created a listing, another model, and so on and so forth. And these models were not talking to each other. So we were losing information. And actually, if you looked at the data, often there was some interactions here. So if someone created a fake account and then created a fake listing, we really wanted to be able to capture that data to accurately capture someone who was suspicious. OK, so the solution we came up with is what we call a meta model. And this is a framework that enables models to share information. So the idea is that a user comes in their first session and they sign up, and we run a model and we say, OK, they have this % chance of being risky. And we send that to our meta model. And then when the user comes back in session 2, when they log in and they maybe create a listing, we have other models. But then those models are now using the information from the meta model to create a more holistic signal. So if someone was a little bit risky at sign up and then a little bit risky at login, we now can leverage the cumulative risk to make a judgment call about whether or not this is a risky transaction. Now, as you can imagine, there are many different activities that we're tracking on Airbnb. Associated with those are many locations, and associated with those are many devices. And so you have many, many dimensions of data here, all happening in a sequence. And this is a great opportunity to use state-of-the-art deep learning techniques to be able to capture that high-dimensional data and more effectively capture fraud and identify new types of fraud that we haven't seen before. So now let's turn to scaling algorithms. That was just one example. We obviously are using machine learning in many, many other areas of our product, and it's important for us to have a system that can make it very quick and easy for us to do machine learning. So what was our problem? It turned out machine learning was a very slow process at Airbnb. It took months to deploy a model into production, and there was no shared infrastructure, so everyone needed to build their own infrastructure, duplicating efforts. And when we looked at some of the external solutions that were out there, even though there are great external solutions, as we've heard about even earlier today, we felt that there would be additional benefit of us building our own system in-house so that we would have deep integration with our data stack and the data tools we were already using. The solution is to build infrastructure to support machine learning models at scale. And because we built this infrastructure, we went from building models and deploying in months to being able to do so in minutes. And that is a huge improvement for our product and enables us to move so much faster for developing machine learning models and enables us to actually do it at all, because in the past, you're looking at, should I do machine learning? Well, it's going to take a couple months. Maybe I should do something else. And now you can really move a lot faster. The way that we did this is we looked holistically at the process of creating a machine learning model, so from data collection to training to productionization to monitoring. We leveraged open source tools as much as we thought made sense, and then we also built our own tooling to integrate it beyond that, to again make it very user-friendly and easy to use at Airbnb. Now, that final point around monitoring, one of the main things we will do is experiment when we launch a new model to see what are the effects of that model. And that leads us to our last section, inference. Now, inference is really around understanding what is the causal impact of what we've done. The primary way that we do that is through experimentation, in addition to other methods. And that's A/B testing, very common now in data science today. However, it often is more complicated than it looks. So let's talk about a problem that we faced in inference. So one problem is SUTFA is often violated. Now, you might not know what SUTFA is. For the economists in the room, you know exactly what this is. But the basic idea is that the outcome for subject 1 should be unaffected by the treatment assignment of subject 2. And this is a fundamental assumption for experimentation to make sure that you get an unbiased estimate of your treatment effect. Let's talk through an example that will help to illuminate this. So imagine that we want to experiment with a new treatment of a pricing strategy with 5% higher prices relative to the current pricing strategy, which is our control. We assign listings to the treatment and control, or hosts to the treatment and control. And what we'll find is that the control will steal revenue from the treatment group because they have lower prices. And so that treatment effect that we're measuring is going to be very different than what would happen if we launched that new pricing strategy to everyone. So this is an issue for us, and it turns out it's an issue for many companies where you have users that you're experimenting with, and you have interactions, right, where it's not independent anymore, and especially in networks. Now, at Airbnb, we had tried market-based experiments in the past, where the real goal is to come up with units where the assignments are independent, so clusters where they'll be independent. And markets was one way to do that because you'd assume San Francisco might be independent from people who are looking for a place in London, and so that could be one way to do it. But we could do better. So we decided to try demand clusters to reduce SUTFA violation. And the insight for this is that if you do a search on Airbnb and you click on a number of places for a given trip, there's something that's similar about those places. They share a similar demand profile. They're in a kind of comparative set. And so we can take that guest trip click session data, combine with the listing data, and create an embedding model using a neural network to represent each listing as a vector, cluster those, and then output clusters of listings that we hope will be based on this demand profile. When we do that, we get some very interesting results. And so you can see here the clusters mapped onto 3 different locations. So for example, in Tahoe, on the bottom right, you can see guests looking for a summer getaway. On the top left, you can see the guests who are looking for a winter ski place. So this is really cool to be able to see the data here, and it rings true. It also helps us to capture coasts. So for example, Copacabana, you can see all the kind of coastline listings. And you can see it go beyond location. So on the right, we have the South Bay. If you look at those purple dots, you can see that some of the purple dots are actually kind of co-located with yellow dots. And what that means is that those purple dot listings actually share something more in common with the purple dots in the more dense area. And so that's like the comparative group you want to use. So now that we have these clusters, we can use them for experimentation and hopefully help to address SUTFA. This continues to be an active area for research for us, so expect more there. Now for scaling inference. In the ideal world, we want to be able to test anything and double the speed of our experiments every time. So one of the problems we have, though, is small sample sizes and low power as a result. So I shared some data earlier. We have 4 million hosts. That sounds like big data. However, if you look at maybe hosts who have gone through a funnel and not everyone makes it through, and you experiment on some later stage of the funnel, that's small data now. If you use clusters like we just described, there are many fewer clusters than there are listings. And so as a result, that minimum detectable effect, the MDE, sometimes can be large, and we're not able to detect significance. And our experiments can take weeks or months because we need to wait to get enough data. The way that we've solved for this, or are iterating on solving, is through variance reduction. And so the general idea here is that we take information that predicts our target metric, and we subtract it out, and then we have less variance, and we're able to get a more precise estimator. And the end result is that we're able to double the speed of our experiments. And you can imagine what a big impact that can have on our iteration cycle at Airbnb if we can double the speed of our experimentation. So that was an exciting area of development, and again, more research to come here, and also a neat intersection of machine learning and using that to reduce the variance as well. So closing notes, I would like to share the Tao of data science. So the first principle is that connecting methods is the path to nirvana. As I mentioned, in all of these examples, you might have noticed there were interactions of analytics, of inference, of machine learning, and it was that kind of combination that really made things happen and gave the progress that we were looking for. And this is a new field, and as we bring methods from different fields, I think we'll see a lot of really cool results coming out of that. The second one is a data scientist is not measured by the cleverness of her solutions, but by the value of the problems she solves. The idea here is you want to be solving problems. Every example I gave was framed as solving a problem. The third point is that the hardworking data scientist is indispensable, but the wise data scientist automates and scales. So always be thinking about how you did a lot of work to do it that one time. How do you scale it so that you don't have to do it again? And in conclusion, I started at Airbnb 6 years ago. Data science was a very new field, and the problems that our team has worked on over the years has truly evolved and changed. And I'm so excited to see it evolve even more in the future, and for this group of women in data science to be part of that evolution. So thank you.